Okay, good afternoon, everyone. Welcome to the second webinar of the European Membrane Society series. I am Maria Grazia De Angelis, and with the technical direction of Professor Marco Stoller, on behalf of the European Membrane Society, I'm here to host this webinar. Today's webinar will be given by a young scientist. I am very proud because our speaker today is one of the winners of the 3 best paper awards awarded by the European Membrane Society last year. And his name is Mohamed Irshad Baig. And he is a final year PhD student working under the supervision of Professor De Vos in the Membrane Surface Science group at the University of Twente in the Netherlands. He joined this group in 2017, and he worked on ERC-funded project, which goes under the name Sustainable and Advanced Membranes by Aqueous Phase Separation. As you understand, the goal of this project was to develop a new aqueous approach for the fabrication of polymeric membranes. Before joining this group in the Netherlands, Irshad performed his studies first in Pakistan and then in South Korea. And in this webinar, he will speak about an alternative and sustainable method to prepare membranes, which does not rely on organic solvents. So now, Irshad, the stage is yours.
Thank you very much, Maria, for this nice introduction. Indeed, it's an honor for me to present my work and share my screen. I can do that. Can you all see my screen now? Okay, so thank you again, EMS, for providing me with this opportunity, and it's an honor for me to do this because we have done this work for the past 3 years, and now it's becoming recognized. And I thank European Membrane Society for inviting me to give this talk about my paper on sustainable membranes by aqueous phase separation. My name is Mohamed Irshad Baig, and I am a PhD student at the Membrane Surface Science at the University of Twente, and this group is headed by Professor De Vos. I started this PhD in 2017, and now I'm almost at the end of my PhD, and that is why I want to show what we have achieved regarding the sustainable aqueous phase separation membranes. As you all might know, that this current methodology, it relies on non-solvent induced phase separation. So all the polymeric membranes that we see, most of them are prepared by this technique. So what happens during this technique is basically you take a polymer and you dissolve it in a solvent, which is such as NMP or DMSO. And you take this polymer solution, and if you want to make a flat sheet membrane out of this, you cast on a glass plate. And after casting, you put it in water. So what happens is that the polymer is insoluble in water. And that is why it precipitates as a membrane, because it does not like water. And this membrane was first developed in the 1960s or late 50s, basically, by Loeb and Surarajan, where they found out that they can make different kind of structures using this process. And well, we have different structures. One of them is called isotropic structures, and the other one is called anisotropic structure. So the difference between the two is that on isotropic membranes, the pore size remains almost the same from the across the cross section of the membrane. But in case of an anisotropic membrane, there is a thin layer on top where the pore size is the minimum, and then the pore size increases from top to bottom. And this process of non-solvent induced phase separation is quite versatile, and that is why we can have immense control over the membrane structure and pore size, which allows us to get different kind of membranes. And these membranes have been long used for different kind of applications. Some of those applications are mentioned over here. For example, the microfiltration, which is basically removal of bacteria or suspended particles from water streams. And the pore size of the membrane ranges from 10 micrometer to around 100 nanometers. So if you have to remove proteins from your solution, then you can use ultrafiltration type membranes, where the pore size is even lower, from 100 nanometers to around 10 nanometers. And also you can reduce the pore size even further to nanofiltration range, which is basically around 1 to 2 nanometer, and that is used to remove multivalent ions and sometimes salts as well. And the other category of non-solvent induced phase separation membranes, the reverse osmosis membranes, which uses really immense pressures to remove salts from water streams. And the pore size is even less. We can say it's quite dense. So these are all different kind of applications of these non-solvent induced phase separation membranes, also counting gas separation, of course. And this method has been used since 1960s to produce commercial available membranes. But there's a major problem with this process, and that is the solvent itself. And most polymers, or the most membranes that are developed, are developed using NMP or DMF. And it has been found out that some of these solvents are reprotoxic and they are unsustainable. And because of these reasons, the European Union has restricted the use of NMP throughout the European Union starting last year. So, but still, there are quite a lot of approaches that were developed over time by different research groups around the world to address this problem. And one of those is to have a different kind of solvent, which is ATBC. So a group in 2013 had this proposed. And another group also did with triethylene glycol diacetate and with styrene, with different kind of solvents that are available. But the problem still remained. There was limited control over the membrane pore size and structure, and also some of the processes were very time consuming and it had additional processing steps. So this is not an ideal approach. There was not a versatile one-step approach to produce polymeric membranes that give the same control over pore size as we saw in non-solvent induced phase separation. So that was still the big research question and a big research point that we had to explore. So what can we do? We can use water as a solvent. No one tried that before. Well, some people tried that, but it was not really a commercial success, not even success at lab scale, not too much, that I should say. So what are the polymers that can be dissolved in water? So one class of the polymers is called polyelectrolytes that are mostly soluble in water. They can be charged, positively charged polyelectrolytes, and there can be negatively charged polyelectrolytes. So if you take these two polyelectrolytes, which are individually soluble in water, and you bring them close together, what you will see is a formation of a polyelectrolyte complex, which looks like this. A polyelectrolyte complex is basically a white, porous, or we can say a dense solid, which is insoluble in water. Now, these polyelectrolyte complexes are not new. These have been around for quite a while now, decades, and they have been used extensively in drug delivery as microcapsules. They have been used for protein compaction. They have been used in flocculation, etc., and etc. But their use in making membranes was first described by Michaels back in 1961, where they used PSS and a polymer known as PWIPTAC to obtain these polyelectrolyte complex membranes. They showed some promising results, but still they were not that useful, and that's why they couldn't catch on. The real use of polyelectrolytes came in 1997 when a research group led by, I'm not sure it was led or maybe it was a scientist called Gero Decker. They invented this layer by layer technique. What they do is they take a piece of polymer, let's say polysulfone or polyether sulfone, and then they dip coat it using two polyelectrolytes. So first they dip it in a strong polyanion, and then they dip it in water, they dip it back in a strong polycation, and that's how they make these multilayers. And this approach is basically used as a coating approach. It's not that we get freestanding polyelectrolyte complex films using this. So how can we do that? How can we achieve freestanding membranes using these polyelectrolyte complexes? So what we did in our work is we used two different kinds of polyelectrolytes. So one is a polycation called polyelamine hydrochloride, which looks like this. And we took a negatively charged polyelectrolyte, which is called polysodium styrene sulfonate, which looks like this. So as you can see that the PAH, I will refer to this as PAH from now on, and I will refer to this one as PSS from now on. So you can see that these polymers have a charge. So the one on the left has a positive charge and one on the right has a negative charge. So if you would mix these two together, you would definitely get a polyelectrolyte complex. And that is what happens. But the thing is, we don't want to have a polyelectrolyte complex in our solutions because as you saw in my first slide where I explained to you how non-solvent induced phase separation works, we need to have a homogeneous solution. So for that, we use a very interesting property of PAH. So if we look at PAH, it is a weak polyelectrolyte. And what does it mean? A weak polyelectrolyte is basically a polyelectrolyte whose charge is dependent on the pH of the solution. So for example, the pKa value of PAH is around roughly 9. So what it means is that if you have PAH in a solution where the pH is less than 9, then your polyelectrolyte will be charged, a positively charged polyelectrolyte. But if you have your PAH at a higher pH, which is above 9, then you will have an uncharged polymer. And this is what we need, because if you mix this now, you take this uncharged polyelectrolyte, which is PAH, and mix it with a charged PSS, because PSS always remains charged. It is a strong polyanion. Its charge is not dependent on the pH, so it cannot be controlled. So that's why we mix it with a weak polyelectrolyte. So what we will have is a homogeneous solution. This homogeneous solution is at high pH, so because we added sodium hydroxide to it to make it uncharged. And now, if you look more closely at this solution, in my work, what we did was we mixed it in a certain ratio, which is 1 to 2 molar ratio of PSS to PAH. Well, this molar ratio is also quite important because it determines how these polyelectrolytes interact with each other. And we also tried quite a lot of different ratios, but apparently this one was working better. I can explain later why this happens. So if we take this polymer solution and we do the same process as we did with non-solvent induced phase separation, but this time, instead of having water in our bath, we have a low pH bath. And why is that? There is a reason for that. The reason is since PAH is charged at lower pH, so if we put this polymer solution, which we just cast, and we put this solution in a low pH bath, what happens is the protons go into the solution, they make the PAH charge, and when the PAH is charged, it finds polystyrene sulfonate, which is PSS, and forms a polyelectrolyte complex. To see schematically what happens over here, I have prepared some animation, you can see. So if you put this, protons go in, PAH becomes charged from a polyelectrolyte complex, and the counter ions are released. So this basically is a polyelectrolyte complex membrane. And if you take it out from the bath and just wash it with water, you can use it for all sorts of applications. So using this process, we did quite a lot of studies. I'm just going to talk about the major studies that we did. So first thing we did was to control the molecular weight of the polyelectrolytes, because that basically controls the viscosity of the solution. And from non-solvent induced phase separation, that is a traditional one, we already know that if you have a lower viscosity of the solution, you will get a faster precipitation rate, and vice versa. So also we tried to change the casting solution concentration, and then we also added chloride to the concentration bath, but I'm going to talk about it later. First, let's see what happens if you use this combination of the polyelectrolytes, which I will be referring to as low molecular weight polyelectrolytes. So if we take these two, mix them at high pH, and then cast it, as I showed before, we get different kind of membranes depending on the polymer concentration. So here you can see on the top left of your screen is a cross-section image of a 12-weight polymer membrane. So this one is quite porous, as you can see. If you see the top surface, you can already see pores ranging from like 2 micrometers to around like 0.2 or 0.5 microns. If you increase the polymer concentration, which is expected, that the pore size will reduce. And that is exactly what we observe over here. So you can see the top surface, the membrane become more denser. But still, it has pores on the top surface. So if we do a pore size analysis on these SEM images, which is actually not an exact estimate, but it will give us some kind of an idea of what the pores look like if we just compare these three. So if we just compare these three membranes that I showed before, we see the pore size is ranging from 0.2 micrometer to around 80 nanometers. So simply by increasing the polymer concentration, we can decrease the pore size of the membrane quite significantly. And if we take these membranes now and check if these membranes can sustain pressure or not, then what happens is that we see that the polymers, the polyelectrolyte complex membrane can sustain pressure up to around easily 4 bars, but we did this test at 0.4 bar of pressure to see that the polymer, the membrane permeates water. And that is an interesting observation because now we can say that this is the first example of a polyelectrolyte complex membrane, a freestanding membrane that has the ability to permeate something. And also it can retain something. So if we did so this is basically an microfiltration type membrane because of the higher pore size and because of the higher permeability. So we did the oil droplet retention test. So the oil droplet is basically, we prepared an emulsion and the droplet size was around 3 to 4 microns. And we let this solution permeate through the membrane at 0.4 bar of pressure, which is quite low. And then we see that the oil droplets are mostly retained. At higher concentration of polymer is retained almost 100%, which shows that the membrane doesn't have defects and well, it can retain something. And this is what it looks like. So this is the polymer solution. This is the feed solution of emulsion before filtration, and that is what we got after filtration. And this is pink because we added a dye to it, and so that we can detect the amount of oil later on using UV-based spectrophotometer. So what I have shown to you right now is a perfect example of an aqueous phase separation membrane that was prepared only using water at high pH and low pH. And this membrane can retain oil droplets, can be used for microfiltration applications. And this is what it is. So now the thing is that can we also prepare different other kind of membranes? For example, ultrafiltration membrane, nanofiltration membrane. So for that, what I showed you previously in this previous slide is that we use low molecular weight, but now what if we use higher molecular weights and then see what happens? And as expected, the molecular weight increases the viscosity. And when viscosity is increased, also you can have denser structures as compared to the lower molecular weight ones. Here I have a small video clip showing how the precipitation actually looks like if you use these high molecular weight PSSPAH solutions. So from left to right, this is the 8 weight % solution, this is 10 weight %, and this is 12 weight % solution. Let me just do this. Well, because of some issue, I think it doesn't play the video. But anyways, what you will see over here is that the membranes precipitate quite quick. So the precipitation rate is quite fast. In like 5 or 10 seconds, you already see complete precipitation. Let me just, yeah, sorry. So here you can see, so there's not quite large difference between the rate of precipitation between 8 weight % and 12 weight %, but still you can see that the membranes are, already looking like a membrane after a certain amount of time. So if we take these membranes out and do scanning electron microscopy on these membranes, what we see is this kind of structures. The top one is cross-section and the bottom ones are top surface images. If you remember the previous slide that I showed you about the SEM images of lower molecular weight one, you can now compare that there are very, very less or very small pores on the top surface. And that is because the viscosity is significantly higher in this case. And that is why it precipitates a little bit slower as compared to the previous one and also has denser structures. So now if we do the pore size analysis of these membranes, what we will see is that the pore size is around 2 to 4.5 nanometers. So simply by changing the polymer concentration from 8 to 12 weight %, we can also tune the pore size of the membrane, again, which is quite similar to what we did previously. So because the pore size is too low, we thought, okay, let's use this membrane for ultrafiltration applications. And the better way to do it would be to use a protein called bovine serum albumin, which is an animal protein. And we prepared a solution of 1 gram per liter at pH 5.5. And yeah, the molecular weight of this polymer is around 66 kilogram per mole, which can give an idea about the molecular weight cutoff of the membrane as well. So if you increase the polymer concentration from 8 to 12 weight percent, the permeability goes down. That is in accordance with the pore size, because the pore size goes down as well. There is more resistance for the water to flow. That's why we have lower permeability. And because the pore size goes down, the retention goes up. And that is what we expected using when we saw the pore sizes. And average retention was about 98% at 12% polymer. So this shows that not only can we prepare microfiltration type membranes, we can also prepare ultrafiltration type membranes by using this simple one-step process, which is very, very similar to non-solvent induced phase separation, except that we don't use any organic solvents in this. So I've shown you that we can successfully prepare ultrafiltration type membranes. The question now becomes, can we take it one step further? And to do that, we can reduce the pore size even further. And how to do that? Because we already exhausted kind of our resources. We can increase the molecular weight, we can increase the concentration of the polyelectrolyte. But also, another interesting thing is to change the condition of the coagulation bath. So to do that, we can add sodium chloride to the coagulation bath. Well, we already had pH 1 there. We just add some sodium chloride and see what happens. And that is what we observe under a microscope if we see these membranes. So when we increase the concentration of salt in the bath, what happens is basically the polyelectrolyte chains have enough time to rearrange and form a denser complex. So when the polyelectrolyte complex is denser, the membrane, as a result, is also denser. And that is what we expected when that is what we observed when we tested these membranes for their pure water permeability. So this image shows you on the x-axis, this is the concentration of NaCl in the bath. The y-axis is the permeability. And on the second y-axis, we have the average retention of different kind of micropollutants. So I'm not going to go into the detail of what kind of micropollutants that we use, but these are commonly existent micropollutants that are basically existing in surface and groundwaters. And the molecular weight of these micropollutants is in the range of 200 gram per mole to around 600 gram per mole. So we take this solution, which is 3 milligram per liter on average, and then we filter it to the membranes to see if the membranes can retain these micropollutants. And what we observe is that at 0%, at the coagulation bath where there is no salt, we don't get any retention because, of course, the permeability is high. There is significantly larger pore size, and that's why everything goes through. But when we increase the concentration of the salt in the bath to 4 molar, let's say, I know it's quite a lot, but I can explain it to you later. We see that the average retention goes up to around 80%. So on average, 80% of the micropollutants are retained by these membranes while having acceptable permeability for a nanofiltration type membrane, which is 2 LMH/bar. So if we take this point, and I'm going to explain it to you over here on the right side. So this is basically a membrane that was prepared in 4 molar NaCl bath, and these are the 8 different kind of micropollutants that we use. So there are positively charged ones, there are negatively charged ones, and there are neutral ones. So this basically, the cocktail gives us a really nice idea also about the charge-based separations that are occurring in the membrane. And because our membrane has a large amount of PAH, because I told you before we have excess PAH, which is 1:2 ratio of PSS to PAH, the charge of the membrane is positive. And naturally, a positively charged molecule such as etanolol will be retained more. And that is exactly what we observed. And other molecules are separated based on either their charges or their sizes. It's basically a combination of both of these processes. But the important point to take from this slide is that by increasing the concentration of the salt in the bath, we are now able to also retain these organic micropollutants, which are quite small in the molecular weight range. So this shows that we also have a nanofiltration type membrane using the PSS PAH system, which is also quite interesting. So, well, let me show you a video here as well, because this is very interesting. To see what happens to the membrane without NaCl and what happens to the membrane at higher concentration of NaCl. You can see that the membrane on the left, where there was no NaCl in the bath, is still translucent, not quite fully opaque after even 30 seconds. But the membrane on the right, which was prepared in high concentration of salt, you cannot see through. And that is because the membrane is significantly denser as compared to the one on the left. And that is exactly why we see different kind of retention behavior and permeability behavior. So this is a nice membrane which can sustain also 20 bars of pressure for an elongated period of time. So we tested this membrane for more than 24 hours at 20 bar, and it still was able to permeate at the same permeability. So what I have shown you now is that by simply using two different polyelectrolytes, a combination of a weak and a strong polyelectrolyte, we can prepare membranes entirely in water. And these membranes can be used for microfiltration applications, ultrafiltration, and nanofiltration applications. So there are quite a lot of parameters that you can play with. So the things that I haven't discussed in this presentation are also the amount of crosslinker in the bath. So if you add crosslinker to the bath, you can also densify the membrane structure. Also, you can play with the monomer ratios of the polymers. So if, let's say you have 1-to-1 monomer ratio, you have 1-to-2 monomer ratio. So of course, the viscosity is different, the interactions of the polyelectrolyte is different, and that is why they can have different kind of structures. So these membranes are entirely prepared in water. Well, one might argue that, okay, well, this is sustainable. You say it's sustainable, but we use quite a lot of acid and bases in our solution and coagulation bath. So, well, this is of course a downside of this process, and I have mentioned it over here, which you should not exclude. So the major limitation of this process is that it uses extreme pH conditions, like from pH 13 to 14 in the solution to pH 1 in the bath. That is, of course, not ideal for large-scale processing. And also, this membranes, the PSS-PH membranes, didn't show any significant salt retention, which are essential for nanofiltration application as well. And yeah, that is why what we did is, okay, we can use a different kind of polyelectrolyte pair. So in our next work, what we did was that we use polyeethylenamine. It's a branch polymer, and it has primary, secondary, and tertiary amines. So the good thing about this polymer is this is available in its basic form commercially. So if you take this polymer, it already has a pH of around 9 to 10. So what it means is that we don't need to add sodium hydroxide to the weak polyelectrolyte to make it basic, to make it uncharged, because this polymer is already uncharged. So what we can do is we can just take it directly from the commercial supplier, and we just directly mix it with the PSS, and we can get a homogeneous casting solution. And that is exactly what we did. We prepared a 25% solution of PSS and pi. And the important thing here is that we cast this membrane or the solution in a pH 4 buffer bath. So this is much different than what I showed you before, because before we were using a pH 1 bath. It is quite acidic. But pH 4 is really mild pH. It's not extreme. It's easy to prepare, and you can just dispose it off. It doesn't really have to be a special treatment for that. So this actually gives you importance of APS as a versatile process, that you can also change different polyelectrolytes, and you can get different kind of precipitation mechanisms based on the process that you use. So under mild conditions, pH 4, we can also get membranes. So we do the similar kind of test. We see, okay, what kind of molecular weights do we have commercially available? What can we do? What can we test? So we tested two different molecular weights of pi. We kept the PSS constant this time. We have lower molecular weight one, which is 25 kilogram per mole, as I have noted here. And we have a higher molecular weight one, which is 750, as I have noted here. So let's start with the first one, which is 25 kilogram per mole. So if we do the same process, we just take the two polymers, just mix them together, 25%, and cast it in the pH 4 bath. We get different kind of structures based on what is the molarity of our buffer bath. So in this image, from left to right, what I did was we increased the concentration of our buffer from 0.1 molar to 0.5 molar. And what it did was it densified the structure and also made the membranes more mechanically stable. Well, that is expected, because at lower concentration of buffer, we have lower buffering capacity, and that is not enough to fully precipitate the membrane. As you can see, it's quite soft here in this image. But when you increase the concentration gradually and make it to 0.5, let's say, and then membranes are quite stable mechanically, and also they are dense, as you can see from this image, with no defects. So this is also a very interesting observation, where we can also play with the ratio in between 0.4 and 0.5 to control the pore size, because in this one, the pore size was quite high. It's not really visible because the magnification is not that high, but the pore size was, I think, more than 20 nanometers, and then we got permeability of more than 130 LMH/bar. So now what we do is we take this membrane, because it looks much denser, and we take this membrane and then we measure the permeability and do the salt retention this time, because it's denser. And we found out that the molecular weight cutoff of the membrane, which is basically a really important parameter for nanofiltration membranes, shows us what kind of molecules can go through, what size of molecules can go through. So this one had a molecular weight cutoff of 230 gram per mole. It's quite low. It's in the nanofiltration type regime. And the salt retention is also quite acceptable with the permeability that we have. It's 4 LMH/bar and in excess of 80% magnesium chloride retention. In this case also, we used a PSS pi ratio of 1:2, which means that there is excess amount of pi in the casting solution. So that is why the membranes were also positively charged. And that is why we see higher retention for a divalent cation over here, magnesium chloride, the lowest one for NaCl and sodium sulfate. So, but the thing is, these retentions are not that great as we would have expected for a nanofiltration membrane. We also did a micropollutant retention test, the same 8 micropollutants, charged, uncharged ones, to see what happens. And we see that we get an average of 70% retention of these micropollutants. The important thing is, if you see the retention of sulfamethoxazole or bromothymol mol to be exact. So this is a molecule which is uncharged, and we see that it's 100% retained, which means that there are no defects. Otherwise, this would have gone through easily because it's the higher molecular weight one as well. So this is a defect-free membrane that can able to retain these micropollutants to an average of 70%. But of course, this is not enough, because we want to have a membrane which is truly a nanofiltration membrane, which has higher salt retention, lower molecular weight cutoff, and a higher micropollutant retention. Because that is something we were struggling with the PSS-PAH system as well. We never had that before. So what we did now was we added crosslinker to the bath. So just the addition of 0.01 weight%, it's quite low GA in the bath, which is very safe to use under lab conditions. We see there is a remarkable difference now between the two membranes. We see a higher salt retention and we see a higher micropollutant retention. And the molecular weight cutoff goes from 230 and now it's around 200 gram per mole. That's a big achievement, and we can call it a tight nanofiltration type membrane. But of course, the permeability goes down. But still, these membranes are really nice if you compare it to the existing commercial membranes. We can say that we have some comparable results with them. So well, these membranes can sustain pressures of around 20 bars, which is more than enough, to say the least, for nanofiltration application. And showing this kind of retention, we definitely think that they are on par, let's say, with the commercial non-solvent induced phase separation membranes. And also with these membranes show around 96% average retention. So this is a standalone polyelectrolyte complex membrane without any coating, without any other treatment. It's just one step casting from high pH to low pH, and that's it. That's why we get different kind of structures. And similarly, if we use high molecular weight now, we get different kind of results. Well, this is a very interesting slide because, well, one would expect that if you increase the molecular weight of your polyelectrolyte, you would get denser membranes. That is what we saw with PSS-PAH, if you remember a few minutes ago. But in this case, it's quite different. We get really high permeabilities, and the pore sizes in the range of typical ultrafiltration to microfiltration type regime. So one may ask that why is this so? This is quite in contrast to what I have talked before. Well, that is because it has to do with the nature of the weak polyelectrolyte that we use. So pi is a branched polymer. So if you increase the length of that branched polymer, then it definitely forms a different kind of complex with PSS. So it's a much more open structure because of the length of this polyelectrolyte chain. If you have a lower chain, lower length of the chain, let's say at lower molecular weight, it kind of densifies into a nice dense complex. That is why we had those nanofiltration membranes. So it's basically to be concise, it has to do with the branched nature of polyethyleneamine, and also the degree of branching is very different for these two, that I have explained in one of my papers, that why this happens. But this is interesting, that now we can just have a high molecular weight polyelectrolyte, and we can prepare microfiltration type membranes that have a permeability of around from 60 lmh/bar to around 120 lmh/bar, and they can retain these N-hexadecane oil droplets to 100% roughly. So this shows that, well, not only PSS-PAH, but another system which is very promising, very exciting, is called PSS-PI system, can also show excellent performance in terms of membrane structure and nanofiltration, microfiltration, or ultrafiltration applications. So this is basically the versatility of the new aqueous phase separation technique, where simply by choosing different kind of polyelectrolytes and different kind of solvents and non-solvents, we can get all sorts of structures. And there are plenty of tuning parameters to play with. So I would say that this is indeed very, very promising alternative to non-solvent induced phase separation. And I would also like to emphasize that this is very new system. So there is a large room for research and development on these membranes, and you can use different kind of polymers, maybe also copolymers, to see different kind of structures, and also one day maybe prepare membranes that can be used that can be prepared in water simply. And that is exactly I'm going to talk about in a few minutes. There is a system, with a promising system, that shows that it is possible to prepare membranes only in water without any pH shift or pH gradients. So the thing is, okay, if we now compare these membranes that I've just showed you right now to the commercially available, not commercially, but I would say that the existing APS membranes that are reported in literature, because APS is quite new field for membranes, and there are not a lot of groups that are working on it at the moment. So, but even though if you take these membranes and you compare it to the ones that are already present, we say that our membranes, the PSS-PI, they perform really nice and superior to the ones that are already existing. So they have higher pure water permeability with a lower molecular weight cutoff, if you can see in this image. And on the right one, there's the magnesium sulfate retention. So we have higher permeability, larger retention as compared to the other ones. This is indeed very promising and very nice to see that APS can indeed give you different kind of structures and nice membranes using only water as a solvent and non-solvent. So if I conclude my presentation now, so I can say that it is possible to prepare membranes entirely in water, and you can have similar control over the membrane pore size and structure as you can have with non-solvent induced phase separation. As I have shown that we have different kind of membranes, all sorts of tuning parameters, such as the pH of the bath, the cross-linking concentration, the solution composition, etc., and etc. And these are just to name a few. There are a lot more things that can be done to tune the pore size of the membranes and just have a nice membrane where you can use it for multiple applications just by tuning the parameters. And of course, I can also say now that it is a sustainable alternative to NIPS, because we don't use any organic solvents, we don't use anything that is really toxic. And even though it uses pH shift, but you can also always neutralize these pH just by adding water or the acid to base or base to acid, and then you won't have a problem by this regarding the disposal of these waste streams. So in future, what we can also do is, in our group, we are also working on developing hollow fiber membranes using this APS approach, and we had some success with that as well. I'm going to share the results maybe later on, because this is still an ongoing research. And also, someone can also prepare a membrane that can be used for reverse osmosis, or probably in future maybe gas separation applications as well. It is also a field which is rather unexplored in this region. And as I have seen, using a different combination of polyelectrolyte for membrane production can yield significantly different results. And there's a ton of polyelectrolytes that are available. And also I can say that there are polymers or polyelectrolytes that are derived by green methods, green solvents, let's say. So someone probably can also use those biopolymers or polyelectrolytes to prepare polyelectrolyte complex membranes. So that will be basically a truly sustainable approach to prepare these membranes. Also, I would like to introduce you to another approach. This is research work done by my colleagues at the Membrane Surface Science group at the university. So not only we use my approach, which is basically a pH shift approach for preparing polymers, you can also use a different kind of polymer system, which is simply a one polymer system, which is P4BP. And this is called the pH responsive polyelectrolyte. So at low pH, it is uncharged and it is charged. And then at high pH, it becomes uncharged, it becomes insoluble in water, and it precipitates as a membrane. So if you control the kinetics of this process, you can have symmetric and asymmetric membranes. So if you are interested to know more about this system, I would refer to you the publication by my colleague, Josh Willett. And also, you can do other way around. So here you have a system where from low pH you go to high pH. You can also have a different kind of system, which is done by my colleague Wouter Neelan at the same group that with me. And he basically used a block of polymers called, it's a copolymer called polystyrene alt maleic acid. And then he prepared a solution with some acid in the solution, and then he precipitates in a different kind of acid where he can control the kinetics and to get symmetric and asymmetric membranes. And these membranes can also show nanofiltration, microfiltration, and ultrafiltration properties, and they are also they can also sustain high pressures up to 20 bars. So this is to say that not only you can prepare membranes using polyelectrolyte complexation, you can also prepare membranes using only one type of polyelectrolyte, which is pH responsive polyelectrolyte. But the another thing is that if you don't want to use pH shift, you can also use salinity change induced phase separation. That is the work done by my colleague Elif Durmaz. And what she does is that she uses two polyelectrolytes, which is PSS and PDADMAC. Both of them are strong polyelectrolytes, and they will always complex if you mix them under normal circumstances. But if you add salt to the solution, so what it happens is that the charges are screened. And when the charges are screened, the polymers cannot see each other, let's say, and then they cannot complex. And when you make this high salinity solution and cast it on a glass plate and then precipitate in normal water, so what happens is that the salt diffuses out of the polymer solution, goes into the bath, and then the polymers can see each other again. The charges are compensated, and then we form a polyelectrolyte complex membrane. And she has shown that these membranes are quite chemically stable, because we already know from literature that PSS PDADMAC is very stable under different kind of chemicals, and can also be used potentially for solvent resistance nanofiltration. And these membranes are also nanofiltration type membranes. Also, we can get different microfiltration type membranes and very stable under high pressure as well. So this is also very interesting work by my colleague in our group at MSc-US. With this, I would like to thank my professor, Professor Vibeke Vos, for of course hiring me and of course guiding me throughout this project. And without his help, it's not possible to achieve these results. And also my colleagues of the APS team at the Membrane Surface Science group, my colleague Josh, Elif, Wouter, Amea, and Lily for their help and support throughout this process. I would also like to acknowledge European Research Council for their funding and support, and of course the University of Twente. This is it for me, and thank you for your attention. I would be open to questions, if any, and thank you very much.
Thank you, Irshad, for this excellent presentation and extremely interesting work. Now we have to activate the chat on YouTube so that people can ask you questions. Unfortunately, we couldn't do this at the beginning, so we will switch off the video just for 1 minute or less, but we can continue talking so that our guests can remain focused. Marco Stoller will switch off the video, and I remind all our listeners and guests today that they have to subscribe to the EMS YouTube channel, and please ask also your colleagues and friends to subscribe to this EMS channel. It is very important, and spread the word, spread the activities of the European Membrane Society. It is crucial for us especially now that we can only have online activities and that we cannot have physical conferences. So to stay together and to increase the outreach of our community is extremely important. And Irshad, as I said at the beginning, probably some of you were not connected, is one of the winners of the European Membrane Society Best Paper Award for his paper published on the subject he presented today. And he was one out of 3 winners, all young and PhD students. And I will probably start with one question for Irshad. You mentioned that this interesting and innovative technique could in principle be applied also to produce gas separation membranes. Do you think that is actually feasible, or do you know of any group that has started working on this?
That's a very nice question. Thank you, Maria. It's indeed a very challenging thing to produce a membrane that can be used for gas separation, because the properties of polyelectrolytes is that when you dry them totally under gaseous environments, they tend to lose their mechanical stability. And that is exactly why it was not used for gas separation before as well. So, but having said that, I think in future, maybe it's a possibility that there comes a technique where you can cross-link them in such a way that even after drying them in gaseous environments, it can still sustain or retain its mechanical stability and can be used for gas separation. But at the moment, I'm not sure if anyone is working on it, and it's quite a challenge, to be honest.
Okay, so thank you. Now the chat has been reactivated and our video also. And we wait for questions from the audience. And again, I remind you to subscribe to the European Membrane Society YouTube channel and also ask your colleagues to do so. I have another question for Irshad. You showed a performance plot where you reported the performance of your membranes in comparison to commercial membranes. But I noticed that your membranes show rather different performances, rather different permeability values, and also different salt rejection values. Was it possible to actually control these performances based on the parameters of the preparation protocol?
Yeah, it's an interesting question. This comparison plot is basically compared to the existing APS membranes, not the commercial ones, because we're not really, not very close to the commercial ones, but still. Yeah, so these are the membranes that are reported in literature by other groups as well. I know one group in Aachen that is working on this, and a group in US is also working on it. So this, of course, can be manipulated. So we can change the pore size of the membrane. We can change the performance of the membrane to have certain properties, for example, lower molecular weight cutoff or a higher salt retention. So this is indeed possible to do that. And as I showed before, we can change this by either changing the pH of the solution, we can increase the cross-linking density in the membrane, or also we can do that by changing the coagulation bath conditions. So there exists quite a lot of number of possibilities to do that.
Yeah, because I saw that the variation is quite large.
Yes.
And, there is a very broad window of possible performances.
Yes, exactly.
Do we have any questions? Not yet. So your future developments are those of improving the nanofiltration membranes, or to trying, or you plan about switching to a different type of membrane, such as reverse osmosis membranes?
The original plan was to have a system where we have mild pH conditions. So that is what we achieved quite recently with PSSPi. And then our aim was to develop hollow fiber membranes. That is basically a big breakthrough for APS, because commercially available membranes are mostly hollow fiber configuration. So our aim now is to just focus our attention and energy to make hollow fiber APS membranes using the promising systems that I showed before. And to say the least, that we have some considerable success in doing that as well. The research is still ongoing, and hopefully in a couple of months, maybe 3-4 months, then we can see the results there as well. But yeah, the effort would be to just make hollow fiber membranes at the moment. But there are different possibilities, of course. Someone can work on developing a reverse osmosis membrane, that as well.
Okay, there is a question online from Bram van Gelder, and he congratulates for your good presentation, and he asks whether you have performed cost analysis compared to current commercially available membranes.
Thank you, Bram, for this excellent question. Actually, I thought about this, but I didn't actually get the numbers. I didn't make this cost analysis at the moment, but that is something that I will do. I cannot say for sure if these membranes are expensive or cheaper than the commercially available ones, but what I can say is that they can be made either at the same level or maybe a little bit cheaper than the ones that we already have. But that's going to take some time, because this process is still quite new. So to answer your question in a short way, I haven't done the analysis yet.
Okay, thank you. Is there any other question? Is the ERC project still going on, Irshad?
Yes, this is still going on, and the funding, I think, is till the end of this year.
Okay.
Yes. So there are, I think, at the moment, there are 5 PhD students working on the project using different kinds of polyelectrolytes for different applications.
Okay, so will it continue, or?
Oh, that is a question for my supervisor. I cannot answer that question.
I'm sure it will. I'm sure it will. It's a very promising work.
Yeah, I hope so.
Okay, it seems that there are no more questions from the audience. Okay. So, okay, if there are no more questions, there is another question. Okay, again from Bram. He's asking whether you have any information about the pH range and temperature, the operating pH range and temperature.
So that's a very, very good question, Bram. So yeah, we did this experiment with PSS-PAH and both PSSPi membranes at different pH. So what we did was we dipped these membranes in different solutions of aqueous solutions of at different pH from 1 to 10 and even 1 to 12. So what we found out is that the PSS-PAH membranes, they are stable from the pH range 1 to around 10. And after that, because we are above the pKa value of PAH, the membranes start to become soluble again, because what we think is the decomplexation of the complex. And that is why the membranes are no longer a membrane after pH 10. And with PSSPi, it's a little bit lower. So at pH 9, they are already starting to dissolve, and they are not mechanically or chemically stable at pHs greater than 8, I would say. But at lower pH, from pH 1 to 8, everything works usual, and the permeability and retention stays the same. So yeah, they can be used from 1 to 8, both of them. And yeah, I didn't do, so the second part of your question is about temperature. We didn't do the temperature study yet. That's something which is interesting as well. We have to look into it, but I don't believe that they cannot work off maybe beyond 50 degrees or something. But yeah, till 40 or 30, maybe they should be fine.
So Irshad, what if I write down here your email address in case anyone is interested in contacting you?
Yes, my email address was also mentioned on my presentation. Okay. I will say it again. So it is m.i.baig@u20.nl.
Okay, sorry. Okay, I am writing it in the chat right now. So yeah, you can repeat it if you wish.
Yes, so it is m.i.baig@u20.nl, and the spelling for Baig is B-A-I-G.
Great. Okay, well done. So I thank our speaker today, and I thank all the attendees. And we have scheduled another webinar for March 3. And there is another PhD student winner of the Best Paper Award. So please fix the date, save the date in your calendar, and don't miss this very interesting series of webinars. For the time being, I thank you all. Stay safe, and I thank again Irshad, and see you next month.
Thank you, Maria. Thank you, Marco.
Thank you. Thank you, Marco. Bye-bye.
Bye.